Without further ado, I give you Dr. Eve Chase.
Thank you very much for the introduction. So as Mr. Meisner said, I'm an astronomer by trade, but I've transitioned out of astronomy into working as a data scientist in the US government. And in today's presentation, I'm going to describe my path through astronomy. I'll share a bit about my research with black holes and neutron stars, and discuss how the skills I gained in astronomy are useful for a career as a data scientist in the government accountability field. But before I get into that, I'm going to start way back at the beginning, and I'll start when I came to TJ in 2009. I was a very proud Froshmore, one of, I think, 12 my year. And at TJ, I did a lot of different things. I took Latin classes and was involved in Latin Club. I did mentoring at a local elementary school. I was involved in rocketry. I did the Student Launch Initiative program. But I had a bit of trouble at TJ finding a scientific field that really fit my interest. Biology, I didn't like too much. Chemistry, I liked. I ended up doing the chemical analysis research lab, but I knew I didn't want to go into chemistry in college. And I started to question whether there was a scientific field out there for me. I knew I liked math, but maybe science wasn't my thing. But one 8th period, I went to the astronomy club and really enjoyed it. I started going back to the astronomy club meeting after meeting. I eventually became president of the astronomy club and took the astronomy classes available at TJ. By the time I went to college at William & Mary, which I really enjoyed, I decided I wanted to tailor my college experience to best suit a career in astronomy. So I majored in physics. There's no astronomy major at William & Mary. And I ended up being the only physics major in my year of college to take every single physics class available. And I also spent every summer in college doing astronomy research. At the time, William & Mary didn't have many astronomy research opportunities, so I spent every summer doing research at different universities. Oh, wow. Getting a preview, through a program called the Research Experience for Undergraduates program. And that's something I recommend keeping in mind when you go to college if you're interested. This is a program funded by the National Science Foundation that pays for students to do research at different universities around the US in the summer. Typically it's STEM research, but there are programs in things like economics or the humanities, and it's funded. So these programs tend to run 8 to 10 weeks on average and pay about $4,000 to $6,000. And you also get to live in the dorms while you're there for the summer. So every single year in college, I did one of these REU programs. I spent a summer at North Carolina State University in Raleigh. That's where I started working on stellar astronomy. And the next summer I got to work at a university in Paris. It's the first time I ever left the US because that's something that wasn't available to me growing up with my family. And in Paris, I started working on gravitational waves. I enjoyed that so much that the next summer I participated in a research program at Caltech, continuing to study gravitational waves. And when I finished college, I decided to keep working on this topic for a PhD. So I moved to Chicago and started my PhD in astronomy at Northwestern University, where I worked on gravitational wave astrophysics full-time. And I'm going to describe more about my research in gravitational wave astronomy and spend maybe 20 minutes or so digging into the science of this topic. So gravitational waves are a completely new field of astronomy, and they've revolutionized what astronomers can do to observe their universe. I'll talk about some of the history of gravitational waves, and to do this, I need to go way back to the beginning, thousands and thousands of years ago. Or for the history of human civilization, people have been looking up at the night sky. You can look at stars and tell stories with them. You can trace constellations in the stars, use the stars to navigate, orient yourself. tell the passing of the seasons. But there's always been a problem with this, and that's humans are limited by what they can see with their eyes. You can't see everything with your eyes. There are objects that are maybe too dim or simply too far away to see. But this all changed with another revolution in astrophysics, which was the invention of the telescope. The telescope allowed humans to see things that were previously inaccessible to them. And one example of this is that around the year 1610, Galileo used the telescope to observe 4 moons around the planet Jupiter. Over the next few centuries, technology continued to develop, telescopes got better and better, astronomers were able to do more and more research, until by the 20th century, astronomers were able to observe the universe in every single portion of the electromagnetic spectrum. They built radio telescopes all the way through optical or visible light telescopes, so light you could see with your eyes, going through to high energy gamma ray observations. And every single portion of the electromagnetic spectrum allowed astronomers to learn something new about the universe. But there's still a problem with this. And that's that people were still limited by what they could see with light. And light can be blocked. There can be brighter objects in the foreground, blocking dimmer objects in the background. You can have interstellar dust in the way of stars you're trying to observe. Or even weirder, there are some stars that don't give off any light at all, like black holes, stars that are so dense that not even light can escape their surface. Gravitational wave astronomy is a completely new field of astronomy that allows you to observe things that weren't able to be observed with light itself. It's kind of like having a new sense. So with electromagnetic observations, you can see the universe. With gravitational waves, you can hear it too. Gravitational waves are waves in space itself. They're waves that change the distance between objects. So if a gravitational wave passed through Earth right now, it would change the distance between me and every single one of you in the audience. So as a gravitational wave passes through the Earth, we each get a little bit closer, then a little bit further away. But it's such a small difference that we'd never be able to detect it ourselves. Similarly, if a gravitational wave passes through the Earth, I'd get a little bit shorter, a little taller, shorter again, taller, oscillating back and forth like a wave. Now, pretty much anything that moves can make gravitational waves, even though those gravitational waves are very weak. So just moving your hands around like that can make gravitational waves. But those waves are so small that you'd never have any chance of possibly being able to detect them. If you want to be able to observe gravitational waves, you need to look at the strongest sources out there. So we look at stars. And in particular, we look at the densest stars in the universe. That includes black holes and neutron stars. Stars that are so dense that they contain a mass around the mass of our sun, but confined into a really small volume around the size of a typical city. And I like this artist's rendition of a neutron star over the Chicago skyline, and it's perfectly to scale. But instead of looking at a neutron star or a black hole by themselves, you need to look at these stars in binary star systems. So to detect gravitational waves, we observe binaries of 2 stars orbiting around one another, where they're either both neutron stars, both black holes, or a neutron star orbiting around a black hole. These systems look kind of like this. So we're seeing 2 black holes orbiting around one another in this video. The mesh below the black hole is showing the curvature of space-time, and we can see a singularity below each black hole. The colors correspond to the gravitational waves being emitted, and we can also see the gravitational wave signal at the bottom of the screen. It looks like a pretty typical sinusoidal wave with some amplitude and frequency over time. But the black holes get closer and closer together as they spin closer and closer together. The amplitude of these waves increases, the frequency increases, until eventually the black holes get close enough together that they release a fury of gravitational waves. and they'll eventually collide to form one final black hole. This system will then release its final energy in gravitational waves and calm down to a final state of equilibrium. This entire process can be detected on Earth, and it's detected with large instruments called gravitational wave interferometers. These images on the right are the two LIGO detectors in the US. LIGO stands for Laser Interferometer Gravitational Wave Observatory. There's one detector in Louisiana and another in Washington State, and they're completely identical. The detectors include one large base station and two arms separated at a 90-degree angle. The arms are both 4 kilometers long, making them some of the biggest vacuums ever made by humans. And inside these detectors, there's a mess of lasers and mirrors that allow for this really precise detection of gravitational waves. So what happens is a laser is shoot down, and it ends up hitting a beam splitter where the laser light is split by 90 degrees. Light travels down the 4-kilometer arm until it hits a mirror at the end and is reflected back. Light from both arms will then be recombined with the beam splitter and reflected on a sheet at the end of the detector that records the brightness of light as a function of time. Since the arms are the same length, the light's in phase, but if a gravitational wave passes through, it stretches one arm and shrinks the other, going back and forth like a wave, and the brightness and dimming of this light at the sheet can be detected and directly relates to the gravitational wave signal observed. So this is exactly how gravitational waves are detected. I worked as a scientist in the LIGO scientific collaboration. I first joined in 2014 after my sophomore year of college, and my work related to writing Python programs to detect these really quiet gravitational wave signals in very messy detector data. I liked this a lot and decided to go back to working in this field the next summer in 2015. But at the time, the LIGO detectors were undergoing about 4 years of upgrades to significantly increase their sensitivity. And for 20 years before that, LIGO had been trying to detect gravitational waves and had no detection. For another 40 or so years before that, there were multiple experiments to detect gravitational waves with no observations. So I actually had some professors in college warn me against going into this field. They thought that no detection would ever happen and that I'd just be wasting my summers working on something that wasn't ever going to occur. But I ignored them. I joined the Caltech summer internship of LIGO interns, and this is all of us here in the summer of 2015 visiting the LIGO detector in Louisiana. And we didn't know it at the time, but just about a month after this photo was taken, the LIGO detectors made the first ever detection of gravitational waves. Sorry, the clicker's not working. Called GW 150914. And this was the first ever detection of merging binary black holes. We can see the signal on the left side of the screen here, and this is an image from the actual scientific publication. In the middle row, we can see the gravitational wave signal, and by looking at the amplitude and frequency of this signal, we can determine the masses of the binary. So we know that we detected 2 black holes of masses of 36 and 29 solar masses. That means 36 and 29 times the mass of our sun. We can also tell that these black holes were 1.3 billion light years away from us on Earth. This was an enormous detection. It was the first confirmation that gravitational waves existed. And a year after this detection was announced, 3 leading scientists in the LIGO collaboration were awarded the Nobel Prize in Physics. By the time I started my PhD in 2016, LIGO was up to 3 gravitational wave detections, which are listed on the screen here, and they're all detections of merging black holes. I started my PhD working on a team of about 200 scientists that worked together to write Python software packages to determine the properties of these merging black holes. So we worked to determine the masses of the black holes, where they're located in the sky, the distance from us on Earth, their orientation with respect to a viewer on Earth, and different properties. I really enjoyed working on this, and in 2017, I was asked to lead data analysis on behalf of this entire collaboration for the 5th gravitational wave detection that ever occurred. And this was also the 5th detection of merging black holes. What was new about this event was that it was the lowest mass binary black hole detection ever observed. And that gives us some more information about the range of black hole properties throughout the universe, which can help us understand how black holes form in the first place. But the detection that was really, really thrilling happened just a few months after this, and that was the first detection of neutron stars with gravitational waves. GW 170817 was the first ever detection of a neutron star merger with gravitational waves. And neutron stars are unique because they give off light. So not only can LIGO observe a gravitational wave signal, but telescopes can also observe light from this system. So what we did in LIGO is work as quickly as possible to determine where these neutron stars merged with respect to the sky. So we could tell astronomers, go point your telescope over there and see if you see any new light that wasn't there in your previous observations. And that's exactly what happened. About 12 hours after the LIGO detection, astronomers pointed their telescopes in a specific region of the sky and saw a new signal that wasn't there before. So this was the first ever multi-messenger detection with gravitational waves, a detection of light and gravitational waves at the same time. And there's a lot you can learn with this. These multi-messenger detections can teach you about general relativity. You can measure the expansion rate of the universe with these observations. You can learn about stellar astronomy, get an idea of how black holes and neutron stars form in the first place. Cosmology relates to this expansion rate of the universe. You can learn about high-density physics. Neutron star mergers are these really dense environments, so dense that you can't replicate their properties in a lab on Earth. So by observing them with telescopes, you can get an idea of how matter interacts at these really high densities. Also, neutron star mergers can teach you about the production of heavy elements. A fun fact is that it's theorized that approximately half of all atomic nuclei heavier than iron are formed in neutron star mergers, with the other half coming from supernovae. So we'd expect that elements like gold and uranium that we find on Earth all eventually came from neutron star mergers. So by observing these sources, we can learn more about how heavy elements are formed throughout the universe. I was absolutely fascinated by this detection. It was just such a revolution in physics that I decided to spend the rest of my PhD focusing on neutron star mergers. And I worked on a few different topics, all related to both gravitational wave and electromagnetic detections of neutron star mergers at the same time. I can't describe all of them today, but I'll say that the main product of my PhD was a tool that helps astronomers optimize their telescope observations. I built an open source Python package that's built around 40,000 computer simulations of neutron star mergers. And the goal is to tell astronomers whether their telescopes can observe these sources or not. Is their telescope able to see a neutron star merger at the distance that LIGO thinks these neutron star mergers are at? Likewise, I used this tool to help promote observations with the most sensitive telescopes. So there's so many telescopes that aren't able to detect light from neutron star mergers that LIGO can see. So it's really important to use the most sensitive telescopes we have to try to observe these signals. And that can include telescopes like JWST, the Hubble Space Telescope, the Nancy Grace Roman Space Telescope, which is going to be in orbit in a few years, and LSST, which is the Vera Rubin Observatory Legacy Survey of Space and Time, which is wrapping up construction in Chile right now. It was also important to me that telescopes don't waste their observations trying to look for a neutron star merger that they have no chance of detecting. Telescope observations are really expensive. Like they literally cost money. So breaking your standard observing cadence to move and observe a different part of the sky is very expensive and also means that science is lost in the process, especially if that telescope has no chance of observing one of these signals. Near the end of graduate school, I was starting to question whether I wanted to keep working on astronomy for my whole career. Astronomy was feeling more and more distant for me, but literally distant, looking at these sources that were millions of light years away, but it also felt further and further away from real people and real problems on Earth. I also noticed that I was a lot more interested in how science got done rather than the science itself. And I was interested in how people organize themselves to get these big scientific projects done. Lastly, I became really aware that science research and astronomy research was funded by taxpayer dollars. I knew that everyday people were contributing some of their money to this research, and I wanted to make sure that that taxpayer money was used efficiently. That's part of why my final project in my PhD related to optimizing these telescope schedules. So with some of these values in mind, knowing that astronomy felt a bit more distant, and just being really fascinated by respecting the taxpayer dollars going into astronomy research, I decided to pivot my career and use some of the skills that I had learned as an astronomer to work as a data scientist in the government accountability field, which means that I work to help the government work as efficiently as possible and to maximize the use of taxpayer dollars all across the government. You all have probably heard the term data scientist, and I'll just try to define it real quick, but it actually means a ton of different things and is used in many different definitions all throughout industry. And there are probably several hundreds of TJ alums currently working as data scientists. But in general, data scientists tend to use programming and statistics along with some data visualization to make inferences on large data sets. So I use some of the statistics, programming, and machine learning skills that I gained in astronomy to search for waste, fraud, and abuse in government programs. And I've done this in 2 different levels of government, one in the local government, in the city of Chicago government, and another position in the US federal government. And I'll describe both of these positions a bit more in the coming slides. So my first position in government accountability was in the city of Chicago government in COPA, or the Civilian Office of Police Accountability, which is something that I think is very important. COPA was founded in 2015 as an independent department of the city of Chicago government. That means it's completely separate from the police department, but is tasked with overseeing CPD, or the Chicago Police Department. COPA does many different things, but one of the main things COPA does is that it collects every single complaint against a CPD employee, so a Chicago police officer, throughout the city. COPA then analyzes all of these complaints and will investigate the most serious of these complaints with the goal of putting out a recommendation related to the police officer's employment status. So that can range from anywhere to saying that this police officer needs a bit more training, all the way to saying that this police officer should be fired or should lose their job. These recommendations are only about employment status, so there's no criminal or civil allegations associated with them. But COPA will frequently get the court system involved for certain allegations. The vast majority of employees at COPA are investigators, so people that look at individual incidents of police misconduct. But while I was working at COPA, I was on a very small team called the Policy Research and Analysis Division. We were mostly PhDs, mixed between qualitative researchers and quantitative researchers. And our goal was to identify patterns and practice of misconduct within the police department and also issue reports related to how CPD could improve some of their practices. The main output of our work was policy recommendation letters, which were publicly available online and have a bit of meat behind them that I could describe later. And one of the policy recommendation letters that I oversaw while working as a data scientist at COPA was that I had full access to all CPD databases that's legally mandated. And we noticed that CPD wasn't correctly recording when one of their police officers quit while under investigation. So you could imagine that that happens a lot. If you're under investigation for misconduct, maybe you'd rather quit and go find another job rather than wait a few months just to be fired. And by doing a data-driven study, I was able to identify a few police officers that had left the Chicago Police Department while under investigation. They weren't recorded as such in databases, and then a few months later, they could reapply for their jobs and be rehired without that investigation ever being picked up. It looked like that misconduct incident had never occurred. So by putting out this policy recommendation letter, we were able to bring this issue to light, and CPD is now working to correct this issue. It's something I'm very proud of, and my colleagues at COPA continue to put out really phenomenal policy recommendations. I really enjoyed working in this government accountability position, and an opportunity came up to move to a new accountability organization that had a bit more teeth behind it to really institute change in the community. So I ended up transitioning to my current role in the federal government in an Office of the Inspector General, or OIG. And there are 74 OIGs all throughout the federal government, and they tend to be attached to a specific agency or department. So the Department of Education has an OIG that oversees work going on in that department and looks for patterns of waste, fraud, and abuse. There are also OIGs for the National Science Foundation and NASA, where part of their job is literally investigating money that goes to astronomy research to make sure that money's being spent correctly. A good tie-in to my earlier work. There are also OIGs at the state level, so the state of Virginia has an Inspector General, and the city of Chicago also has an Inspector General, which plays a role in police accountability and overseeing the work that COPA does. Of the 74 different federal OIGs, there are about 14,000 employees, where only a few hundred of them are on the data side of things. The few employees looking at data analytics and data science try to write algorithms to broadly look for patterns of fraud in the agencies that they oversee. And I think a really cool statistic is that the federal inspector generals have a huge return on investment. So in a previous year, the OIGs had a budget of about $3.5 billion, but through their work, they were able to identify and remedy over $93 billion of waste and fraud in the federal government, which I think is a really amazing statistic. I work in the OIG directly tied to the General Services Administration, which is an agency that plays a large role in the general functioning of the government. GSA does a ton of different things. They manage almost all government buildings and property, so there are thousands of buildings across the US managed by GSA. GSA is responsible for a lot of the technology in the government, including software purchasing, and they also manage a large amount of spending that the government does as a whole. So almost all purchasing, regardless of what agency of the government it is, will go through GSA websites or databases. And GSA also records and keeps track of all companies that receive government funding or do business with the government. So as a data scientist, that means that I have a tremendous amount of data that I can work with, and I work on a team that tries to identify patterns of fraud with companies that are selling goods to the government. I can't describe any specific projects I work on, but it generally relates to companies trying to get a better deal from the government, and this can include collusion or wire fraud. So one thing that'll happen a lot is maybe there's like 5 companies that are the only companies that sell a certain good to the government. They can all get together, decide to artificially inflate their prices, so the government's forced to spend more money to get that good, which is wasting taxpayer dollars. That relates closely to some of the values I described earlier. I use a ton of data science skills that I've gained all throughout my education. So that ranges from doing programming. I'm programming almost every single day, and that's something that I learned as a TJ student for the first time. I've used skills that I gained as a physics major at William & Mary and in my astronomy career at Northwestern. And this includes things like machine learning, doing different spatial and statistical analyses, and also placing an emphasis on data visualization and data storytelling so I can explain my work at an accessible level. In general, all of these skills that I've gained as an astronomer help me in my career today, even though I don't necessarily work on astronomy anymore. I'm really proud of my research I described earlier with black holes and neutron stars, but I'm even prouder that I've been able to take those skills and apply it to something that helps with the community. So as a wrap up, I'll say something that I wish someone told me when I was a TJ student, and it's that the skills that you're learning at TJ are valuable, and that what you're focusing on in TJ doesn't necessarily need to be what you focus the rest of your career on. It's perfectly normal and natural to change fields throughout your career. What you major in college doesn't need to be what you study for the rest of your life. Whatever your senior research lab is doesn't need to relate to what you major in college, and that's perfectly okay. Just know that the skills you're gaining along the way are useful no matter what you decide to do. So I'll wrap up by giving a congratulations to the seniors here, wishing you the best of luck on your research presentations later, and I'm enjoying going to listen to some of the presentations. Thank you very much. Is there any time left for questions?
So we have about 2 minutes of questions. If you'd like to submit a question for Dr. Chase, whether you're here in the auditorium or in one of the other classrooms, we've set up a short little bit.ly link that you can submit a question to. So if you take out your device and go to bit.ly/tjSTAR 2024, all lowercase, you can submit a quick question, and then I'll give you 10 seconds to do that, and then I'll start asking some questions.
Wait, I was gonna ask you how loud, like. But that's like an interesting question. Wait, I still don't get like the actual physics between like how like, you know how like, she talked about like when they put like the 90-degree like whatever the light sensor or whatever, and then like they reflect it back off, and then like the gravitational waves would like affect the wave of like the light, and like when it.
Here's our first question coming in. This is from a 10th grader in room 26 with Dr. Dalcero. How did you know that you wanted to pursue astronomy to begin with?
I don't remember settling on astronomy, but when I look back, I found something I wrote as a junior in high school saying I definitely wanted to study astronomy, so apparently I was pretty set on it. But I think it is just enjoying the astronomy classes I took here at TJ. I loved going to the planetarium. I thought it was really fun. I loved every single lecture, and I decided, okay, if I like something so much, I should keep doing it.
All presentations previously scheduled for lecture hall will now take place in Tesla Commons. Everyone, please check my opportunity.
And maybe one more. Here's a question from another 10th grader in room 82. What is the most valuable thing you learned at TJ? And what would you say to us about college?
The most valuable thing I gained from TJ as a whole is not what I learned, it's the people you meet along the way. So it sounds cute, but also going to William & Mary, There were so many TJ alums at William & Mary, and I've had a large network of people to talk to and also gain insight from for jobs going forward. So your TJ network is very valuable, even if it's 10, 20 years after you leave TJ.
All right, so Dr. Chase will be around all morning, so I hope if you see her in the hallways or if she comes to your talk, you continue to ask her questions. Can we give her one more round of applause? We also have a small gift for